Last time we talked about principle of least action, and that got us into Lagrange's equations as being a local principle that comes from this global principle of the critical point in the space of all possible curves of the actual physical path. So that's kind of where we left it. And then I also said that Lagrangians have this ambiguity to them where if you add a total derivative, it doesn't change anything. And that was called the gauge invariance. So that's going to end up being important for generating canonical transformations. So from last time, we had the principle of least action, or really it's principle of stationary action or critical action. That's the thing that gave rise to Lagrange's equations. But we could also arrive at Hamilton's canonical equations through the principle of least action. And I put it in these scare quotes because it's not always necessarily least. That's not part of it. It's just that it's a critical point, and there's no condition on the second derivative. So what was it for Lagrange's equations, right? It was, we take the action, which often we write as S, integrate over the Lagrangian over time, and we're looking at the critical point. So that means you look at first variations. This delta S means take first variations, and where there are first variations that equal 0, that gives you the equations of motion. Well, we could do the same thing, but for writing L using H. So this uses the kind of reverse Legendre transformation. So we could write L, but now substituting in for L, we'll write it this way. It's a sum from 1 to n, pi qi dot minus h as a function of q and p. So this is writing L, but in terms of the Hamiltonian. So we use the reverse Legendre transformation if you want, and then we'll set that equal to 0. And this is following, there's a really good section of that Hamil book on A Student's Guide to Lagrangians and Hamiltonians. So this is from section 4.4 of Hamil. We have in general, if we're thinking now of just the usual Euler-Lagrange equations, this sort of general thing that didn't necessarily have anything to do with mechanics. This is now a integrand. So we'll just write this as a function phi. And what does it depend on? It depends on q dot, p, and p dot. So we're just going to use the earlier techniques, ones that we talked about last time in the calculus of variations, and treat this like it's just a normal calculus of variations problem. And we'll write the Euler-Lagrange equations for this. So here we're assuming that q, p, q dot, p dot are all independent variables. Well, there's q and p, and then there's q dot and p dot, which, yes, depend on the time rate of change. But we have this set of variables, okay? And time is the independent variable. So from what we had before, this would have Euler-Lagrange equations. How many of them? Well, there's 2n, where n is the number of degrees of freedom. So the 2n Euler-Lagrange equations for this is what? I'll break it up into two different parts. First, I'll do the q's and then the p's. So there's d dt partial phi partial qi dot minus partial phi partial qi equals 0. That's just the Euler-Lagrange equations for this writing phi, like we have it up here. The index I goes from 1 to n. And what do we get? Well, what's the explicit dependence of phi? There is no dependence on p dot, but that doesn't matter here. So if we were to take this derivative, partial phi partial q dot, the only thing we'll pick up is a pi dot for that corresponding thing. So we'll have d by dt of pi. So it's like we pick out that one thing, and then minus partial phi partial qi. Well, where is the explicit dependence on QI? It's only in H. This would be minus partial H partial QI equals 0. So that's the writing only half of the Euler-Lagrange equations. We'll write the other half next. But this is what we would get. All right, now just move things around. This becomes an equals. And instead of writing d by dt of pi, we'll just write it as pi dot. And whoa, lo and behold, that looks like half of the Hamilton's canonical equations right there. So it's kind of weird that the Euler-Lagrange equations for this thing is Hamilton's canonical equations. You get all the big names all at once. All right, so what about next part would be p's. So we'd have that d by dt partial phi partial pi minus partial phi partial pi. So this is d by dt partial phi partial pi dot. And there's no explicit dependence in this equation on pi dot. So this just gives us, that's just 0. What about pi? So we'd have minus, it's like we pick out from this sum, we just get qi dot minus of minus partial h partial pi equals 0. And then you just rewrite that. And what does it give you? It gives you the other half of Lagrange's equations. Qi dot equals partial h partial pi. So, what do you know? So we recover Hamilton's canonical equations. We're still somehow writing the Lagrangian. Just like, okay, that's weird. And so we've written the Lagrangian to look like that in terms of h, just due to the Legendre transformation. So that works. And now we'll do more with this. So this is where we get to the generating function approach of canonical transformations. And this is also in the Hamel book, the same chapter, which I like. I think it's the same chapter. Section 5.2. And we'll first do it for 1 degree of freedom, and then say this generalizes to n degrees of freedom, because it's just easier with 1. So we're going to think first of just n equals 1 degree of freedom. And where we could use either of 2 generalized coordinates, little q or big Q. Little q or big Q as the generalized coordinate to describe our system. And we're so sort of backing up and writing the Lagrangian. If we had a Lagrangian written in terms of q, the little q, the Lagrangian would be a function of q dot, and possibly time. And remember what we ended with last time. We said you could write L in different ways, where you've got an L prime, just a different Lagrangian plus a total derivative of some function f. Well, in this right-hand side here, L prime could be a function of the other q, big Q. And remember, big Q, you can write big Q in terms of little q, and vice versa. That's why they're generalized coordinates. So we could also write the Lagrangian that way. And now for the function f could be a function of either little q or big Q or time. And now we can integrate. If we integrate s, so get the action, we'll integrate L, Q dot, time, dt equals the integral of both things on the right-hand side. but we'll split them up. L prime big Q dot time dt plus integral of df dt dt. And we could write this as, if S is the integral of L, then we'll say the integral of L prime is S prime. And what is this? This is the integral of df, because we've got derivative of f with respect to time integrating over time. So we've got the sum of these two equals S. So that's how the actions are related in the sort of old variables, the little q's and the big q's. And now when we take the first variation, so if we were to go through the process that we did before and put the little deltas, so it'd be like delta S equals delta S prime plus delta of this integral of f, which I think we could view as just delta f. The key thing is, what we get for this delta f thing. We'll get partial f, partial q. It doesn't matter kind of which one you do. Remember, I'm being loose with the notation. This is going from some initial time to a final time. So let's just write it as here's the final time. We went from T1 to T2. Delta Q T2 minus partial F partial Q delta. And this was at T1 delta Q T1. But the way that we've defined this variation function, the delta, either little q or big Q, both of them will vanish at the endpoints. And so that's why we get delta S equals delta S prime. They'll both be the same. So one of these would be, you get the Euler-Lagrange equations or Lagrange equations for the little q with delta S equals 0. And this would give you the Euler-Lagrange equations for big Q with delta S prime equals 0. And the total derivative of f, the function f, contributed nothing. Total time derivative of f doesn't change the first variation of the action. That's the action integral. And so it doesn't change the dynamics. You could depict it in two different ways, maybe this little q or big Q, but it doesn't change what the dynamics really are. And it's just worth noting F has units of action. And the action integral, which is energy times time. That's just something to note. All right. So that was writing it in terms of the Lagrangian sort of formalism. So now we're going to write the integral of the Lagrangian over time using the Hamiltonian function in the Legendre transformation. So we're just going to write that action integral like we did up above at the beginning today, using the Hamiltonian function and the Legendre transformation. It's kind of the reverse of what we usually do. We usually, when we're trying to construct the Hamiltonian, we start with a Lagrangian, but now it's like we're doing the reverse, but they're both called Legendre transformations. So what do we get there? We get delta S is delta integral over time of, now we're writing L, but using the Legendre transformation. So P Q dot minus H Q P, and we're going to let the possibility the Hamiltonian depends on time. All right, so this is just another way of writing L, just to remind you. So we've got that. And the first variation equals 0. So that's the principle of least action coming in. And so what's this going to do? This is going to give us the equations of motion, as we saw up above. And we could equivalently write this in terms of the big Q and whatever big P is. So there's big P, big Q dot minus, and I'm going to write the Hamiltonian as a function of the big Q and big P in time, not as H, but I'm going to call it capital K. I think before I may have called it H bar, but calling it capital K, kind of to match the notation of that book. Oh, and what else will we do? That's L, or think of it, this is L prime. We could also add on, because there's this ambiguity, a total derivative. So let me just add on a total derivative plus df dt. Setting that equal to 0 also gives the equations of motion, just maybe described in different coordinates. These integrands are equal. They're equal, so we could just set them equal. So just take the thing that we're integrating over, set them equal. So the first way we wrote it was in terms of little p and q minus h, q, p, and t. And then the other way is in terms of big P, big Q, and then that total derivative. So we're going to base things off of this equation. I'll call this the starred equation. We'll start next to it, where we haven't said what F could depend on. But now that we've written things in terms of Q's and P's, the F, it's a scalar function. Kind of nice. It's nice dealing with scalar functions. The scalar function F could depend on any of the variables, meaning F could depend on little q, little p, big Q, big P, and time. And so the process that we're going to follow, we're going to use that start equation up there to find a canonical transformation from the little q's and p's to the big q's and p's. So that's sort of where things are going. Going both ways. Okay. We're first just going to suppose some dependence on F that makes things easier. Okay, so let's initially suppose that it doesn't depend on all of these. Let's just suppose it depends on little q and big Q. And for reasons I'll say below, I'm going to write this as F sub 1. We're saying there's some unknown scalar function, F1. It only depends on little q, big Q, and possibly time. And now let's take its total derivative. D F1 dt equals what? Now we use the chain rule. There's a lot of chain rule that's going to happen. Partial F1, partial Q, dq dt, which is just q dot, plus partial F1, partial big Q, q dot, and then partial F1, partial T. Okay, and now we're going to plug this into that start equation up above. So what do we get? P q dot minus H Q P. Maybe I'll suppress this just to make it easier to write. P q dot minus K. And now all this stuff, partial F1, partial Q, q dot plus partial f1 partial big Q dot plus partial f1 partial t. So we have an equation. We're going to rearrange things. So rearrange. And you'll see where this is going. We want, right, we've got two things that multiply little q dot. We've got two other things that multiply big Q dot, and then we have whatever's left. So we're going to rewrite it to kind of collect terms. Okay, so P minus partial F1 partial Q. Those are times Q dot. I'm putting everything on the same side, so there's going to be, we're going to set this equal to 0 eventually. What's the next term? Plus, I think it's a minus actually, if I know what's going on. Capital P plus partial F1 partial big Q times Q dot. Then plus minus H plus K plus partial F1 partial T. We want this to hold for all possible little q dot and big Q dots, right? And the whole thing equals 0. So that means each of these individual things in the parentheses have to equal 0 separately. So this equals 0, right? This equals 0. And this equals 0. So what does this imply? Once we've gotten to this point, now we just sort of rewrite these things we've set equal to 0. So P equals partial F1 partial Q. Big P equals minus partial F1 partial big Q. And the Hamiltonians are related this way. K equals H. Oh, there was a minus sign up here, sorry. K equals H plus partial F1 partial T. So what have we got? This is true. This is what we get for any F1 that's a function of little q and big Q and T. Any function, these over here give a canonical transformation. And we would say it gives a canonical transformation generated by this scalar function F1. You know, how is that? If I've got some scalar function F1, and I'll give an example. What will this give? This will give a P, that is, take partial F1 partial Q. That'll also be a function of big Q, little q, big Q in time. So that means little p is little p as a function of little q, big Q in time, which you can then invert to give big Q equals big Q as a function of Q, little q, p in time. So it's kind of weird the way that we're defining things in terms of other things, but the whole system holds together. And so similarly for big P, P equals minus partial F1 partial Q. And what is F1 a function of? Little q, big Q, and T. This gives, you don't have to invert it. It sort of naturally will give it to you. Q, little q, and then big Q. But instead of big Q, right, big Q is a function of little q and p and t. So this will just become a function of little q, little p, and t. So then you get the canonical transformation that you're looking for. So let's choose an example. Let's just pick something simple. Always nice to have an example. So here's an example. I'm looking for an F1 that's a function of little q, big Q, and t. So I'll choose just, how about little q times big Q? and just forget t. That's the simplest thing. So if I do that, then what? Let me follow this. Big P equals partial F1 partial big Q. So it's minus Q. Okay. Little p is partial F1 partial Q, little q. So that gives big Q. And these could all easily be inverted to write the, big Q and big P equal some function of little q and little p. What is that? Well, big Q is just P, and big P is negative Q. And if we had transformed the Hamiltonian, K equals H, there's no effect due to explicit dependence on time. So that's our transformation. So this is a legitimate canonical transformation. In fact, it's a linear one. We could write it this way, right? QP, and we recognize this matrix, or hopefully we do. This is the canonical symplectic matrix, and I think this is a transformation we showed before, where it's kind of rearranging, even with that minus sign, it's rearranging what is a momentum and what is a coordinate, just sort of showing that you can do that. So you got to have that minus sign though, or it doesn't work out. We could do another one. This, remember the idea that canonical transformations are independent of the particular Hamiltonian. So this might be useful for some Hamiltonian. It's more useful as just sort of illustrating that the Q's and P's sort of lose their identity. It's not like things are truly a momentum, like there's no mass times velocity going on. It's just, at this point, it's just mathematical manipulations. But then if we return to the simple harmonic oscillator example that we've done a few times, maybe it'll be easier to think about. So here's another example. This is the spring mass again, or the simple harmonic oscillator. All right, and what was that? For this, we have a Hamiltonian, Q and P. And it is, if I write it the way I wrote, once I finally figured it out, 1/2m P squared plus m squared omega squared Q squared, right? That was the Hamiltonian. The motivation when we talked about ignorable coordinates in the Hamiltonian formalism is we'd like to transform this to a new Hamiltonian that doesn't depend on one of the two variables, either Q or P. I want to transform to a new Hamiltonian K that doesn't depend on Q. There's no Q dependence, capital Q dependence. Another way to say that would be partial K partial Q equals 0. So how can we do that? Let's try a generating function. And I'm just going to give a generating function that I know works, okay? And you might, well, how'd you find that? I don't know. It works. The way of constructing it, where you're sort of guided by, well, we want sines and cosines and things so that something cancels, is kind of the more systematic. But this is just showing here's a function, and it's not going to depend on time. Here's a generating function, m omega over 2 little q squared, so the old coordinate, and then cotangent of the new coordinate. We're just assuming this. Like, there's no systematic way. I've just assumed it, okay? And we're just going to see that it gives the same transformation as before. So if you take partial F1, right, this is, we follow that recipe up above of which derivatives we have to take. This is partial F1, partial little q, and we get m omega q cotangent big Q. And then big P is minus partial F1 partial big Q. And then you got to look up what the derivative of cotangent is. Just no picnic. At least I don't like it. 1 over sine squared Q. Big Q. And then you do a little bit of algebra, and multitude of sins can be covered over by just saying a little bit of algebra. I'm not going to say it's trivial. Maybe it is. You get Q equals square root 2 capital P M omega sine big Q, and P equals square root 2 M omega capital P cosine Q. And that's the same transformation as before. Following the recipe for how do you transform, because our function F1 doesn't depend on time, K in the new coordinates is just going to be the same, just written in the new coordinates. So if we were to write, what do we have? We have 1 over 2m, and then p squared gives us, we'll get 2m omega p cosine squared q. There's these 2m's seem to cancel. Plus, now what? 2p m omega, move over this plus sign. We got m squared omega squared over 2m. The m squareds cancel, just 1 omega cancels, 2's cancel, sine squared q. So then what does this equal? We can pull out an overall omega times p cosine squared q plus sine squared q, which is 1. That's cool. Because we had the same canonical transformation as before, we knew how the Hamiltonian would turn out. It's very simple. And notice, okay, what we want, partial k partial q equals 0. Yeah. So then everything that we did before would follow. The Hamilton's equations are super duper easy. Q dot equals partial k partial p. So it's just omega, a constant. Big P dot is minus partial k partial q, but we know partial k partial q by design is 0. So this is 0. So dynamics are kind of boring. And that's what we want. We want to turn things that look nonlinear and crazy into things that aren't. So if you start with some initial condition, it's just going to be flowing to the right with the rate of omega. And then if you wanted to, you could transform back via these equations into what the original solution was. It looks nice and it's useful. This is sort of a bizarre aside, and you can do with it what you want. I don't know how many of you have studied quantum mechanics. If you've done something with quantum mechanics, maybe you've studied the energy and momentum of a photon. So photons are the particles of light. They have an energy. Well, I mean, so a photon, right? It's got some kind of wavelength, but you could also think of it as having a frequency. It has a frequency omega. And these photons, they have an energy E, which is h bar times omega. Or maybe writing it more suggestively, omega times h bar. If you compare with what we've got up here, like, oh, huh. The generating function approach works in n degrees of freedom. And it's not, hopefully it's not that difficult to see it, but so for example, F, if we had an F1, that's just a function of the old Q's and the new Q's. What will we get? Right, it's a function of little q1 to little qn, big Q1 to big Qn. And everything holds, right? And just for notation purposes, I'll be writing the set of all little q's as little q, the set of all big q's as big Q. This subscript 1, this follows a numbering convention of at least Hamill's book, and different books will have different conventions. So be careful. So this might be called like a generating function of the first kind. It is, I guess, useful to see what Hamill's numbering scheme is. So this is Hamill's numbering scheme. If it involves little q and little p, so we're making a little table, and then big Q and big P. So if you have an f that's just a function of little q and big Q, you put a subscript 1. You say that's a generating function of the first kind. If it's little q and big P, generating function of the second kind. Little p and big Q, generating function of the third kind. And then both p's, little p and big P, that's generating function of the fourth kind. And like I said, different books have different numbering schemes. So don't think this is some kind of universal thing. Plus you can combine them, and that's just going to confuse you like crazy. Like different sets of coordinates, you could do different things. So if I were to summarize, right, these are the 4 main kinds, and we'll summarize them here in a table type thing. For all of them, the energy transforms the same. And by energy, I mean the Hamiltonian. The Hamiltonian transforms as k equals h plus partial f. And now I'm leaving this subscript sort of, that's just I. So the Hamiltonians all transform the same, but then we'll start with what we had up above, q, little q, big Q, and t. And the way that things work out when you do that procedure we did up above, so pi is going to be partial f1 partial qi, and then big pi is negative partial f1 partial qi. And then there's the other 3 different types. What was this one? Function of little q and big P. So here, big pi, right? The things that aren't shown, this always just does it in pairs. And then you have partial derivatives that define the other 2. So this would be partial f2, partial qi, and then this becomes big Qi is partial f2, partial big pi. There are 2 more. What was this one? A function of, we usually do like the old coordinate first, big P, no, little p and big Q, and possibly time. Qi equals minus partial f3, partial pi. Pi is minus partial f3, partial qi. And the generating function of the 4th kind. Sounds ominous. This is p and big P and time. Qi is minus partial f4, partial pi. Qi is partial f4, partial p, big pi. Okay, so those are the sets of rules. And when I said you can combine them, it's not like you have to do this purely across the board for, 1 through n. you could have a combination, like maybe you wanted to have an F. I'm not sure why, but this might come up. You might want to do an F where it's some combination. Okay, like F1, Q1, big Q2, and time plus, oh no, big Q1 plus F3 of P2, Q2, right? And then the separate rules would apply for those sets of variables. But in the end, you'll have a canonical transformation. We can look at some other examples. Yeah, let's try an F2 example just for fun. Here's F2. And I'll pick like the lame thing I did before of just, well, let's just combine them. You might be like, why are you doing this? Why don't you just have them as a, little q plus big P? So there are some additional conditions and you should read about them. But, for example, you need this, the partial derivative here has to not equal 0. And I'm not going to go through the conditions for all of them, but just think of them as, okay, it's going to have to be like quadratic at least, or nonlinear. So P, if we just follow the rules here, P is partial F2 partial Q. And oh my goodness, that just gives us big P again. Huh. And then big Q is what? Partial F2 partial big P. And that gives us little q. If we combine these, it looks like we just have the identity. Little q equals big Q, and little p equals big P. If we're really fancy, we write it as a matrix to really convince ourselves. It's just the identity. It's just the identity. Okay, you would hope that the identity is a canonical transformation. And yes, indeed it is a canonical transformation. You could even verify that the 2 by 2 matrix times J times 2 by 2 identity matrix transpose, still the identity, so this equals J. So that's M transpose equals J, which was one of the conditions of a canonical transformation. So wow, that's okay, that's cool. What could we do with this identity transformation? Well, you could do an interesting set of transformations called near identity transformations. And these are a hoot. Near identity transformations. What do we mean by that? Well, and if you want to look, it's in Hamel section 5.4.1. Okay, so we know what the identity transformation is. It's little q, big P. But now let's add on something small. So epsilon, which is small, times another, let's say, unknown function, capital G, that's a function of Q, and big P. Epsilon is small. So just by the fact that epsilon is small, when you take the partial derivatives, you're going to get something that's close to the identity, right? P equals partial F2 partial Q. It's going to equal big P plus epsilon partial G partial Q. And big Q is partial F2 partial big P. That's going to be little q plus epsilon partial G partial big P. We can rearrange to get kind of write this in the form of looks like a near identity. Big Q equals little q plus epsilon partial G partial P. And big P equals little p minus epsilon partial G partial Q. So that's the near identity transformation. And now let's make a particular choice of what G is. Let's choose G to be the actual Hamiltonian governing the dynamics. Like, well, how can we do that? Well, G, Q, big P. This would be, we're going to set it equal to the Hamiltonian. You might say, well, how can we do that? We could do this because it's near identity. We can do this since big P is close to little p. So whatever our original Hamiltonian was. You might say, well, what do we use for epsilon? Well, a natural thing might be, how about a time step? A small time step. Like we're going to be stepping forward in time. We can do this, and we can sort of summarize big Q can be identified. Maybe we'll do it this way. Yeah, it can be identified as little q, but advanced a little bit in time. And what you can't maybe see this yet. We'll see it. Big P can be identified as little p advanced a little bit in time. How is that? Well, let's just take what we have up here for the near identity transformation, but plugging in that G is actually the Hamiltonian describing the system dynamics. And we get that big Q equals little q at time t plus dt partial h partial little p, because little p is close to big P. So the partial derivatives will be the same. So this means this is q plus dt. What is partial h partial p in canonical Hamilton's canonical equations? This is q dot. So what we're getting is something that looks like the Euler solver for ODEs. It's just a first order integrator. So that's where we get this identification of, well, big Q is little q at t plus dt. And same big P is little p at t plus dt. And it's P time t. But now there's a minus. We're going to absorb the minus elsewhere. So this is plus dt minus partial h partial q. And what is minus partial h partial q in Hamilton's canonical equations? It's p dot. So this is p time t plus dt p dot. So this is a first order in time numerical solver, also called an Euler solver, or Euler integrator. If you've learned about numerical integration, this would be like the first type of integration that's used. It's not the best, but it works. And all this came from using F2 is QP plus epsilon H, the Hamiltonian. But what does this mean? If we think about what does this mean? This means that at least over small times, the solution to the trajectories of Hamilton's canonical equations is also a canonical transformation generated by this generating function that includes the Hamiltonian. If that made sense, not sure. So if we just think in the original coordinates Q and P, and we've got some initial point, we'll just say this is Q at sometimes T and P at sometimes T. The Hamiltonian vector field is going to be pointing in some particular direction, right? That's the Q dot P dot vector, but we know what that is. That's partial H, partial P minus partial H, partial Q for some Hamiltonian. And if you step forward a little bit, so this is, you sort of flow for just a small time. This is epsilon times q dot and epsilon p dot. You get this new point, which is q times t plus dt, p times t plus dt. You keep doing that. Well, now at this point, the vector corresponding to q dot and p dot is slightly different. And that's just how an Euler solver works. It just sort of keeps going. And if you connect all those points, you'll get some kind of solution curve to your Hamiltonian, passing through that initial condition. We can call it the solution curve, or really this is a solution map, because we're saying q times t and p at times t, and then we're taking that and mapping it forward, map forward to where are these things a little bit later, t plus dt. So the solution map, or I think I referred to it before as the flow map, at least over infinitesimal times. And if it works over infinitesimal times, you just sort of link them all together and it works over larger times. The flow map of Hamilton's canonical equations is itself a canonical transformation. And that's kind of weird. There's canonical transformations everywhere. Often the solution map gets written as just phi of t. So it's like you take phi of t of some initial conditions, and that would give you, if you start here at q0, p0, as you vary time, right? T at 0 means the identity, and t for later times, it's like you're tracing out more and more of this curve, and who knows what the trajectory does. So the flow map for any time t is a canonical transformation. So these canonical transformations form a big theme because they're kind of all over the place. So I'll summarize with the big picture of canonical transformations. Now that we've seen a bunch of things about them, we haven't yet done everything. So the big picture is that we'll prominently put canonical transformations. And what are they? These are, it's kind of weird what they are. Are they changes of variables? Yes. Also, the solution map is a canonical transformation. So there's lots of things. So it relates to, we could just start enumerating them. It relates to allowable changes of variables. And you can find them using generating functions. And the space of all possible generating functions is large. There are the solution map, meaning the solutions of Hamiltonian systems are also canonical transformation. I mean, the solution map means it relates how not just one trajectory, but like entire sets of trajectories can change. So that's related to that earlier stuff I said about, you take blobs in 6-dimensional space and project them. It has something to do with being a canonical transformation. So the solution map, or I think it's more common to call it a flow map of the dynamics, is a canonical transformation. What does this imply? This implies there's a certain kind of geometry for the solutions, which we've hinted at already. And it holds not just in 1 degree of freedom, but in n degrees of freedom, where you have 2 n-dimensional things. Sometimes this has been called symplecticness when we're talking about properties of the solutions rather than properties of the equations themselves. That's the term used by one of the books, Sancerno and Calvo. What else? What kind of motivated the canonical transformation things? We want to do changes of variables, but we want to do changes of variables that simplify a problem. Can be used. to simplify. That seems good. But also classify, perhaps, systems, Hamiltonian systems. And on this simplify theme, that's what we're going to have to get to next time, not right now. You can find the best possible, I'll put that in quotes, canonical transformation to most simplify a given system. And this will depend on the problem. And it depends on just what the original Hamiltonian is. And this is the subject of Hamilton-Jacobi theory. To give another hint of what that means, it's based on using a generating function, where a time-dependent generating function, where the Hamiltonian in the new coordinates, which we've above called k, remember that's h plus partial whatever the generating function is, partial t, we want that to equal 0. And that's what it's all based on. You want it to always be 0. So you can rewrite this as a PDE where you're solving that PDE. But we'll have to get to that next time. Time's over.